Good afternoon, everybody, and welcome to the third Thursday of the month, third Thursday of February 2021. This is Dylan Miner, and I'm here with Igor Kuvayev. Today, we're going to talk to you guys a little bit about ROGII's machine learning. Now, uh, like most of you guys, for the last, it feels like maybe almost 3/4 of a decade now, I've been going to conferences and I've been seeing these commercials, and everybody's talking about machine learning and about data analytics and AI. And I feel like some of the different companies, when they're using these terms, they're using them to mean different things. And sometimes I don't even think that the way that they're using them is actually machine learning or AI. So Igor, to get us started off, could you just explain what is meant when we use the terms machine learning and AI?
That's a great question, Dylan. Yes, so in very simple words, machine learning is when machines are learning from a certain experience, right? So they're learning from something that has happened already. And the best example of machine learning that we always use as a sort of reference case would be Facebook. How Facebook can, build a machine learning system that can recognize photos. Why? Because Facebook has a huge experience, has a huge database that we helped Facebook to create. It's the database of our names and our faces and our age. That what made Facebook face recognition so great, but it actually explains how generally machine learning works. Now, on the other hand, there is a very broadly used term, AI, artificial intelligence, and machine learning is actually one of the ways how we can sort of achieve AI. And honestly speaking, the definition of AI is too broad. It's basically machines doing certain tasks by themselves. And there are lots of definitions of that of AI. So that's why we prefer to stick to machine learning, because it gives us a very clear boundaries. I mean, what exactly we're trying to achieve here. Oh, Dylan, you're on mute. Still on mute. Yes.
Yeah, my space bar trick wasn't working for me. I guess it's my own fault. Okay, that makes things a lot clearer. Now, with machine learning, as the machine itself is learning, is getting the results from its own algorithm and learning from it, is that something that requires human interaction? Is it human independent, or does whether humans are involved not matter at all?
It's quite, I mean, especially with the modern tools like Python, like all the libraries that were developed under Python, it's quite automated. So I wouldn't say you just push a button and that's it, but it's fairly easy to use even for like regular geologists. Now, the question is data. In order to achieve a good machine learning result, you need a good you need a good high quality input and a good output. Again, coming back to Facebook case, the reason why Facebook was successful is because they have a great input data set.
Got it. That makes sense. Okay, I think we're clear on what the definition is going forward here. So if you'd like, go ahead and start your presentation.
Great, thanks, Dylan. So basically, today we want to talk about machine learning and machine learning that we, ROGII company, we use in our technology. Basically, something that some of you may be using already, even sometimes not knowing it. And before I start, or actually in my very first slide, I would like to just say why machine learning, right? Why we want to use machine learning in our products? Why can't we just use something much easier and simpler and much more understandable? And most importantly, we don't use it because it's a buzzword. We use it because in some tasks, and I will show you later on why exactly in those tasks we can use only machine learning. It's the only technology that helps us. So again, a very simple explanation. Where, for the tasks where we need machine learning and where we don't need machine learning. So let's say to the very left, I have a very sort of simple black box, perfectly black, color equals to 0. 0 for programmers is black color. Both sides are exactly the same. So like absolutely perfect black box. So if we just say, if color equals to 0, A equals to B, this object is black box. It's, simple and easy for computers to understand. Now, in reality, when we're dealing with black boxes, we're going to be dealing with something like that. It's a picture of black box, somebody's holding it, it's not perfectly black. it's not very well defined. So in those cases, we do need machine learning to actually for a computer to identify that it's a black box displayed on that picture. And the way, again, very, very simplistically, the way machine learning works is exactly the same if-thens, but instead of just having one or two of them, we have millions or billions of those if-thens. And some of those if-thens are not really understandable for us, because once we create that machine learning system, once we go through the learning procedure, it comes up with those if-thens. They call it decision tree. And if you just go there and try to, from our human standpoint, from our logic, understand what's going on there, you won't be able to understand it. Nobody will be able to understand it, but it will work. And in that particular scenario, most likely the first if then will be something like, if edges are straight and if majority of color is great, and then, million of other ifs. But at the end of the day, it will allow us to identify that it's a black box on the picture with quite good quality. Again, assuming that we have a good training data set, we trained our machine learning system, and we were able to see the results, and we're sure that it's giving us a good result. A very good example of machine learning would be Google search. Google search, believe it or not, is exactly the same if-then statement, but if you just look at that formula that they use, it's 1 gigabyte. So it's 1 gigabyte of if-thens, billions of if-thens. And when you type in, your keywords in Google, it's just going through that formula. And as I said before, those if-thens, those decision trees that are used by machine learning, they're quite fast. That's actually one of the advantages of machine learning systems. So they're quite fast. So as you type your, what you're searching for in Google, even though it's 1 gigabyte formula, it's already sort of giving you answers because machine learning works fast. So with that definition, before I switch to the actual applications of machine learning, let me maybe say a few words of sort of framework. So what's our framework for ROGII products, how we implement in machine learning in our products? And I think that's critically important because as we go forward, as we progress with those technologies, it's getting easier and easier to develop machine learning technologies. Literally almost every person these days with basic knowledge of Python can come up with machine learning model. And we see it happening in many operators and service companies already. A lot of different people from, actually not necessarily data scientists, just, very commonly regular geologists, drillers, reservoir engineers, they develop their own code. So they basically develop their code. And the biggest question is not whether there is a code, but whether, how we can actually use that code, right? How we can deliver that code to real-time operations. And majority of our products, majority of ROGII products are used for real-time operation, drilling, geosteering, production prediction for if we are talking about Starfrac. So how can we sort of merge both of these words? People coding in most commonly Python and consumers of the product that would like to get the results in real time. And this is how we achieve that. We have the products that we are currently developing and using, Solar RTM, StarSteer, Starfrac. We have our cloud database. And majority of our code, majority of our machine learning code that I'll be talking today, that we're using, it's actually running under, actually majority of that is developed under Python, not always, but most of it. But it's running under the Solar Cloud. Why it needs to be run under the Solar Cloud is because we need a real-time update. Drilling is a real-time procedure. So as we get the new data, we need to make sure the results of that machine learning is delivered in real time to all the consumers of the final product. So with that, it's probably a little bit boring slide, but if we're talking about a particular machine learning technologies that we're going to be talking today and where we are using those. So today we'll be covering AG. AG actually stands for Assisted Geosteering, the tool that helps us to geosteer the laterals that we constantly developing and improving. I guess we're going to have a good chunk of discussion about AG. Solar box data filtration. For both of these technologies, for both of these applications, what we're actually using is something called neural network. It's also a sort of machine learning technology. Then RTM status definition, drilling status definition, and key performance indicators. RTM projection to the beat. For that, we use something called boosting. And the last one, StarFrag, we use actually a wide range of technologies. Even though there are lots of sort of strangely looking words there, it's all decided for you. So I will show you how it works. We'll go through that live, and you'll see that actually it's a very neat and nice tool that sort of does machine learning as you work in StarFrag. Now, the very first one that we want to discuss today would be assisted geosteering. How do we use machine learning in our assisted geosteering? Now, sort of disclaimer here, we, as I mentioned before, we don't use machine learning because it's a buzzword. We use it only in those applications where we think it's beneficial, where it can make things better, faster, and more user-friendly. In assisted geosteering, we use a lot of, I would say, regular procedures, if you can call them that way, different, log-to-log correlations, fairly, standard mathematical procedures. But where we found machine learning particularly useful is actually vertical portion, vertical well log correlation. We call it assisted geosteering in the vertical part of the well. Why we think machine learning is the best technology there is because, and actually I'm going to repeat it throughout the rest of the presentation many times, is because our data, unfortunately, our geoscience data is bad. It's noisy, it has a bunch of data quality issues, it's not perfect. Actually, if you kind of go back in time, so the task that we're trying to solve here is actually quite simple. It's vertical well log correlation. So we're just trying to say, okay, if there is a geological formation top here, as an interpreter, as a human interpreter, I am correlating this gamma to that gamma. So the same geological formation top will be here. So the first, I was actually looking in the literature before this webinar, and the first paper, the pioneering paper on that technology, believe it or not, was published in 1964. So kind of forever ago, and basically it goes through very basic, well, maybe not very basic, but some technologies, how you can automatically correlate two vertical wells with each other, how you can identify the tops. Very good and comprehensive paper. Now, there is a paper actually that showing the technology for well log correlation that most of the packages that I've seen on the market are using as of today. And again, it's not super new, it's 1987. And actually that's, we use something very similar to that technology with actually the biggest difference is in order to correlate two wells, instead of just using standard mathematical formulas, we use machine learning. And again, the reason why both of these approaches didn't work for us, or actually they kind of worked, initially we used it, but then as we looked at our data, and our biggest problem is that we're dealing with real-time data. All of us who just steered the well in our sort of life, we all know that real-time data is much worse than data from the memory. It has noise, it has a bunch of issues. So we identified, or we found with experience, that those two approaches and these 1987 approach didn't actually work with noisy data. What are the typical issues of our real-time data? So first of all is actually the worst one is NWD2 change, when suddenly the scale increases by a substantial value or multiplier. And this is a big deal because, I mean, there is no way or no good logical way how we can explain to computer, why this is not a geology change, why it's something, totally related to the tools or actually the procedure of the drilling.
And if you think that's hard, you should try explaining to a directional driller that we need him to log the last 20 feet again so that we can make a one-to-one correlation to get those logs to line up. That's not easy either.
Right. You need to explain why you need to waste the time on that relog procedure. Now we have noise, which is fairly easy and good thing to deal with. We also have our magnificent geology. So geology can vary from here to here, which also creates a lot of issues for just standard procedures when mathematically we are just comparing two logs with each other. And on top of that, it's mostly our geosteering problem, but for high inclination angles, for inclination, I would say generally above 60 degrees, or of course, depending on our geology and area, we have thickness differences. Also, these type of problems are not good for the approaches that were developed back in 60s, 70s, 80s. Now, so in order to solve all of that, we came up with this methodology. And if you actually run assisted geosteering, and if you don't have it, talk to us. We can give you a trial, of course. If you run assisted geosteering on your wells, you will see that in the vertical portion of the wells, if you pick those tops, even with very noisy data, even with poorly looking wells, even with the data where sometimes people struggle, it works very good. I mean, we're really proud of what we achieved with that technology. But how we actually developed it. So remember at the previous portion of the previous slides, I said that in order to come up with machine learning, we need to train it first, right? So we actually need a training data set. And in this case, actually training data set is something easy to get. We were, again, in simple words, what we were doing, we were just taking a log, or actually a series of the logs, and we were corrupting that data. So we are adding a noise, adding different gamma ray scale changes, stretching and squeezing the gamma ray, just basically, corrupting the data as much as we could. And then we were using these two data sets as a training pairs, right? So we basically said that, hey guys, this top or this position, this geology is the same as this geology. So, and we were training neural network using that data set. And the result of the training works in a way that now we can send two pieces of the log to the neural network, and the neural network will tell us, okay, it's a good match between those two pieces of the log, or it's a bad one. And here is how we display it. We basically send, say, a log from the type well, send a log from the vertical, from the lateral well, and then it goes kind of, log piece by log piece and compare it with all the log pieces from the other well. And if it's a good correlation, it shows us red color. It's not something you can see in StarSteer, of course, but it's sort of how the algorithm works. If it's a good correlation, it shows you the red color. If it's a bad correlation, it shows you blue color. So it's sort of similar to that image produced by, shown in this paper in 1986. The biggest difference is in order to come up with those colors, we use machine learning. We are not using any mathematical formula anymore. And as I said, it works quite well, and you can test it in StarSteer with assisted geosteering right now. So now, actually going forward, it's not something that we have in StarSteer, but what I said before, also the beauty of all the machine learning technologies is that they work fast. So our well-to-well, vertical well-to-well correlation that we developed as a part of our assisted geosteering, it's super fast. We're talking about, maybe less than a couple of seconds to process a well, which is much faster than any other well correlation that I've seen in my career before. And probably we can make it even faster. So once we developed it, we actually thought that, hey, now as we have this great well-to-well correlation, why can't we just have it in the vertical track? It's not available in StarSteer yet, but it's coming. So we believe in the upcoming future, which is coming soon, you will have an option to quickly and automatically correlate the vertical logs of vertical wells pick the tops on the vertical wells automatically. So that's sort of assisted geosteering and how we use machine learning in assisted geosteering.
Now, Igor, you know this is coming. This is something that I've been hoping for since this assisted geosteering idea first came up. So as an old ops geo, an old geosteer here, one of the big things that we run into in areas where faults actually exists at the subseismic level is trying to identify them. Currently, the way that at least I always did it, and I think most geosteers do it in their career, is that you're looking at your data set, being aware that there's a possibility of faults. But you often can't see it immediately. You can't, at least you can't see it in the gamma, and you're only really aware of it a little bit later on, when all of a sudden your correlation has you in a position where you didn't think that you were. At that point, then we go back and we start looking at all the drilling parameters and trying to find a spot where we may have crossed that fault. And of course, there's always the old joke about the geosteerer's fault that is actually just that there may have been some incorrect geosteering previously, and there was a fault thrown in there. So is there any way that we could use any of these machine learning techniques to help kind of either whether it's AGU, StarSteer, or something else to be able to pick where those faults happen in real time? Do you see that as a possibility?
I think, Dylan, it's a great question. And what's specifically good that you actually describe the procedure of how you as a human, right, identify those faults as you geosteer the lateral. What is important in your description is that you're not only looking at the gamma ray as a experienced geosteer, right? You're looking at actually many things. You're looking at the nearby wells. You're looking at drilling data. You're looking at possibly seismic data or structural maps. So it's a complex data analysis that you do as a human in order to come up with those faults. Possibly, I mean, there is a good chance that if you have only that particular lateral with only gamma ray, not knowing where is it geographically in which particular area of the world you're working with right now, you would not be able to identify those faults, or you would be much worse at identification of at that fault identification. And that's actually the problem, the AG problem that we're dealing with right now. Because AG, even though it actually works good, and in the upcoming release of StarSteer in a month, I think it will be amazingly good. I strongly recommend you guys to try it. But that's actually exactly the problem we're dealing with right now, because everything AG knows is the survey and the log. And actually, it's only one log, gamma log, and the typo, of course. And as any technology, it's as good as the data you have as an input. And here we're sort of going into more into domain of another buzzword that people like to use these days, is big data. Because in order to, as we think, in order to be able to identify faults and actually teach AG to be very good at that fault identification, we need to go into the big data world, right? So we need for AG to know the geographical position of the wellbore, neighboring wells, drilling data, some neighboring wells, drilling statistics. So is it possible? Yes, and I think eventually we'll be there, but we need much more data and we need much more learning.
Well, I personally will be very, very excited when we get there. I think that will solve a lot of the mysteries, and as a geosteer, like you sometimes, especially now with remote geosteering becoming more and more popular, you're already looking at 2 to 3 wells, maybe more at the same time. So to be able to at the same time be watching every one of those drilling parameters and looking for that combination of drilling parameters that might indicate a fault before you recognize it in your gamma correlation, I think that would be really powerful to be able to respond to it hundreds or thousands of feet earlier than we already had. So I guess my vote on where our development efforts should be focused going forward. But anyway, thanks for the answer on that one, Igor.
Absolutely, I totally agree with you, Dylan. I mean, as much as we can, we need to help geosteers to identify all kinds of geosteering / drilling problems in real time. That's the whole goal of our development. Now, The next technology that we'll be talking about, it's fairly quick one, and actually, interestingly enough, very much related to the previous one that we discussed. So, as we all know, actually, let me start from a different angle. We all want data in real time. We all want to get surveys and logs specifically in real time as the data is acquired by the tool and pushed up to the surface. Now, the common problem that we're dealing with is if we connect to WithML server, typically the data that we see there is honestly speaking, doesn't look very good, let's say politely. So then we are, either looking at the data and just patiently waiting for MWD person to send us the filtered data. And if you talk to MWD person, most likely he or she is just sitting at the rig and just manually filtering the data. There is no good procedure to get nice and filtered data in real time. The reason is because the filtration is not filtration of that MWD data is not a very good and linear process, and not something that you can use, not something you can code with simple mathematic formulas. Why? It's basically shown on these examples. I just took a random real-time log. I believe it's log from Permian, but I guess it doesn't really matter. And if you zoom in on those logs, you can see a bunch of funny problems. So there is a fake interpolation, for example, between the samples, which of course is not right. And actually that's a big problem because filters, they can't recognize it. Standard filters that people use these days. Also, there is a very typical MWD noise when what is coming from MWD is just some spikes of a standard gamma ray value. We'll also have some MWD spikes here, and actually maybe 2 or 3 additional types of noises. And we all know, or at least those of you that use StarSteer know, that we have nice despiking averaging filters in StarSteer that we can use. It helps us to get real-time. It helps us to better work with that real-time data because they, I would say, filter 90% of the problems. But in reality, I need to say honestly here, there are some types of data issues that those filters cannot handle or not handling very well. For example, see these constant interpolation that filters don't understand. Those spikes here, series of spikes that are too hard for filters to filtrate, and again, a couple of others. So that's why we actually using it's not released yet, but it's coming as a part of RTM feed. But we'll be using machine learning to automatically filter out all of those problems, all of those real-time data problems. And again, the way it works the same way as the previous idea. We have our initial data, and of course, we're going to take nicely looking and good data. We're going to make sort of bad data out of it, and we're going to use those 2 data sets to learn as a learning data. And with that, we'll be able to filter the data on the fly, real time, and something that you'll be able to use, and it will be much better than our regular, standard WithML outputs. So the next technology I would like to talk about, it's actually quite interesting one, is RTM rig status definition. And some of you may have seen our real-time monitoring, RTM, that is available as a commercial product already. It has lots and lots of features, but really, what is our real-time monitoring? It's why we have real-time monitoring. We have it for real-time drilling optimization. In order to optimize something, first thing that we need to know is actually what is happening out there. So the first sort of cornerstone of real-time drilling optimization is to be able to identify, understand what is the drilling status, what my rig is doing right now, what my rig was doing 10 minutes ago, what kind of procedures and steps my rig was performing over the last, say, 24 hours or day versus night. And this is the visual of it. It's basically what you will see, or what you're looking at when you're using RTM is your rig. We call it rig status, but basically what your rig was doing over the last. So it's a day shift versus night shift, and all of those colors, they correspond to different types of drilling activities. Then you also have key performance indicators, what kind of in-slips time you had, and many other ones. And the only input that goes into that system is so-called surface rig channels, right? It's different sensors that are located on the rig, and they're recording information of what my rig is doing. And the problem that we are solving or solved with machine learning is how we can convert those input channels, rig channels, and here is the list of all the things we have at the rig side, or all the sensors we have at the rig side. How we can convert those channels into these so-called rig statuses, and here are the rig statuses that we can identify. And again, in the perfect world, coming back to that example of well-log correlation that was invented back in the 60s, yes, in a perfect world, we can use something that is called binary logic, which basically a good example of binary logic is displayed here in the right bottom corner. If bit depth is higher than bit depth, say a few seconds ago, and bit depth equals to hole depth, if flow rate is lower than minimum flow rate, RPM higher than minimum RPMs, then my rig is drilling. You can pretty much define those type of excuse me, those type of if-thens for any status, and in a perfect world for perfect data, it will work. Of course, it doesn't work all the time. Our data has all kinds of issues. First of all, is data quality, noise, blank spaces in the data, no data values. The biggest problem for us as a sort of international company, we have a lot of wells in Permian Basin, say in Argentina, where everything is meters and totally different units, different units and thresholds. Another thing, I'll talk about it a bit later, drill pipe oscillation and in-slip status. So all those issues, as well as a few other ones, made us to develop machine learning rig status identification instead of just using the binary logic. And to my knowledge, we are the first company that are using machine learning for those rig status identification. Here are some of the typical issues that we encounter. Again, why we cannot use just standard if-then statements here is, for example, this is how it's real data, how my hook load is behaving. It's honestly speaking, it's a nightmare, because now we're trying to, from this data, we are trying to understand when my hook was loaded, when it wasn't loaded, basically yes or no. But you see, even my zero is not always zero value. So there is a so-called different threshold as we drill the well. And of course, the hook load is different. It depends on the depth of the well, depends on many other things. So we need to take into account, we don't live in the perfect world. Same happens with actually many other things, but surface RPM is not an easy thing to deal with. Here is a histogram of surface RPM from a real well. And you can see that we cannot just say that, hey, my surface RPM has to be 0, because 0 is actually quite wide range of numbers here. It can be up to 2. But of course, if it's such a low surface RPM, most likely it's actually technically 0. So pure binary logic is not a solution, unfortunately.
So it seems to me what you're saying is that if in a perfect world with perfect data, binary logic would be sufficient. But in a real operational world, we have to deal with the imperfections of the data set. And that's where the machine learning really cranks in and saves us time and makes things even possible that wouldn't otherwise be.
Absolutely. Or, I mean, potentially we could use a binary logic, Dylan, but then we would have to, put you in front of the computer and constantly, set those thresholds for every particular parameter. and tune them as we drew the lateral.
Sounds like overtime to me.
Yes, I don't think you will be happy with that. Another actually big thing for rig status and identification is drill pipe oscillation. For those of you who are familiar with modern drilling process, now when we're sliding, we are no longer just keeping two-phase constant. We actually oscillate drill pipe to reduce friction, increase the drilling efficiency, and just improve a lot of other things. From rig status identification, it's a nightmare, because instead of just saying, hey, if RPM is 0, then it's a sliding, we have, this sort of rattling behavior that looks like noise. Again, a perfect task for machine learning and nightmare task for binary logic. Another one, I mean, it will be quick here, but it's basically how we can identify in slip status. Don't want to talk a lot about it, but in simple words, there is no good binary logic definition for in-slip status. It's too complicated, too sophisticated to identify. Perfect task for machine learning, and we use machine learning for that. So yeah, that's about RTM rig status. So that's technology that works already, has been implemented. If you use RTM, you can see those rig statuses, and those rig statuses are calculated using machine learning. Another technology that I wanted to talk about today, before I switch to StarFrag, it's only one slide. It's quite exciting. I think a lot of companies are working on that. We are also working on that. Not available yet, but will be available. We have some positive results. We think we'll roll it out quite soon. It's basically, as a GSTer, yes, I do have my survey data. And if you're using StarSteer, you know that in StarSteer, you can calculate your projection to the beat based on number of different parameters. But in reality, what we want is to have my projection to the beat, my beat position in real time. And that beat position should take into account my rotary trend, my motor yield. And unfortunately, both of those parameters are quite variable along the wellbore. They vary in time because of the beat wear, because of other things. They vary with geology. They depend on many other factors. So what we want to achieve here is a technology that, of course, will never, ask you any silly questions or won't require any human input. But basically, it will take real-time drilling data. Of course, if you're using RTM, if you are streaming your real-time drilling channels into Solo RTM, it will take that data, will automatically, of course, split the well into different statuses, because we need to know where the well was sliding, where the well was rotating. And based on that information, come up with the most likely we're going to use boosting, but we'll see a boosting model that will be able to predict or actually calculate first rotary trend and motor yield, and based on those two parameters, calculate projection to the beat in real time. Because I think we're sort of in an ideal position here, since Solo has both drilling data and the geological data from the GST results. So we can merge both of these data sets to come up with the most reliable projection to the beat information.
That looks amazing. That's amazing right there. You said that we expect to be able to have something like that for people to see some point this year?
Yes. This will happen this year.
Okay.
We already have some. We're sort of on the second slide of my presentation where we have a Python code. Now the question is how we can transition it from Python code on, sort of Dylan's computer into something that everybody can use in real time, right?
Yep.
Now, the last thing that I actually wanted to show you live, because I think it's quite exciting technology, is our magnificent StarFrag. And it won't be any sort of long StarFrag demo. I would like to focus on specifically machine learning technologies that we use in StarFrag and why, again, why we use them. And for those of you who don't know, StarFrag is the tool to, it's a multi-well analytical tool that allows you to, first of all, combine and put together your statistics for each particular well. Actually, first of all, for each particular stage, completion stage, then it's going to the well level. We have statistics per well, and then we correlate that statistics to production and come up with useful trends to optimize your, first of all, to predict your production and optimize your development, your field development. And this is a very common problem that we are, as an industry working with unconventionals dealing with these days. We have a lot of wells. For each of those wells, we have lots and lots of parameters. Of course, it's much more than I have it on my slide, but if we want to simplify it, it's well length, total proppant, total fluid, stage and cluster spacing, porosity, or any geological parameter, spacing, timing. And then we have a production that actually essentially an outcome of all of those parameters, right? Because we know how much the well produced, say, in a year or in 2 years, or what's the EUR number. And there are a bunch of tools that you can even use right now, as long as you have the spreadsheet generated, which, if you do it manually, it takes a lot of time. In StarFrag, it's pretty much one button click or even no clicks. There are a lot of tools that can, build a machine learning model that will predict your production. So then, if you know what's all of these parameters for upcoming well, you can come up with production value. What is different about StarFrag is actually we were able to sort of surpass the biggest limitation of all of these machine learning systems. And the biggest limitation is a backward connection. What's the back connection? If we explain it in simple words, Facebook can give you the name from a picture, but if you type in the name, it cannot give you the a computer-generated picture of that person. It will be able to give you only the picture that was taken by that person, but it won't be able to give you, a brand new picture of that person. So it doesn't work backwards. And this is actually the biggest problem of all of those machine learning prediction systems, which is very critical and very important for that production prediction. Because yes, as long as we know that I'm going to drill a well with certain length, certain proppant, certain fluid, it can give me the expected production value. But it cannot tell me what's the best well that I can drill in certain area. And today I will show you how machine learning, how it helps us to sort of surpass that limitation, how we are solving that limitation. As far as particular technologies that we're using in StarFrag, here is the list. If you don't mind, I don't want to read through it, but we are using a different type of techniques. And I'll show it to you in a second. It actually doesn't ask you which one you would like to use. It simply, runs it and automatically, not notifying you, it picks the best one. As far as training models, and for all of the, technologies that I showed you before, I explained you how our training model works. In StarFrag, we use the actual data. So in order for StarFrag to work, we need at least, I would say, 50. I would recommend at least 100 wells loaded. So as long as you have 100 wells and you have, say, production for those 100 wells, then as a training, it takes 80% of those wells, predict production from them, and then verify that prediction on the remaining 20%. Then as a next step, it again takes 80% for the training and another 20 as a sort of testing data set, but that 20 will be different from the previous 20. And then it goes 5 times. So at the end of the training procedure, we have 5 machine learning models that were trained using different data sets and tested using different data sets. And then we merge all those 5 machine learning models together to come up with the best and the most reliable result. with that, let me switch to StarFrag and actually show you how it happens live. So if we just, let me hide this. So if we just looked at the main window of StarFrag, we have our wells loaded. This is a fairly small project. It's a public data, which has actually a lot of limitations that we don't like, but it's a public Canadian data. Thanks for Canada, at least, for sharing the data. And for these wells, we have all the completion information. And of course, we have geosteering data. We have those wells are located on Solo. So once those wells were geosteered, we can just open StarFrag and see them as is. So we don't need to do any additional actions. So again, what StarFrag can do, it can automatically extract all of those parameters per well. So each of those wells, even though they named a little bit weirdly, we renamed them in order to, not to confuse operators. But they have all of those parameters which are just extracted totally automatically from Solo database, like total number of stages, total proppant, fluid, completed lengths, 12 months, something we loaded from production data, 12 months production per well. And we also, because we have geosteering data and we have type wells, we were able to extract, again, automatically extract the porosity, average porosity within the completed volume, right? So we have that, we call it a geological variable, but in reality, it's my porosity of completed rock, which is quite low for this particular formation. Why it's important? Because this is actually our geosteering parameter. Because if I'm not very good geosteer, I won't be able to stay within the zone. My overall porosity will be lower. If I'm better at geosteering, I am 100% in zone, my average porosity is higher. And as we go forward, I will show you whether it, makes sense or it doesn't make any sense to stay in those higher porosities. We can actually quantify the result of our geosteering using this machine learning approach. So what I'm actually doing in StarFrag, and this is something I pretty much will show you live right now, is basically we tell StarFrag which parameters I want to use to as my production drivers. So what are the parameters that can potentially predict my production? And the most common ones would be stage spacing, fluid concentration, proppant concentration. So this one, sorry for the naming, this is actually our average porosity, and completed length. So those parameters, as we think, are the best ones. Why they are the best ones? Because each of them correspond to a specific thing, and most of them, they don't correlate with each other. And as a target variable, I have my 12 months production here. Now, when I push this button, build model right now, basically what it will do, it will build those 5 machine learning models. It will first of all automatically select the algorithm for machine learning, build those 5 machine learning models, and come up with the average ones. And what is, as you can see, it works quite fast. It's done already. And in addition to it, what is actually something, very new to StarFrag and something that allows us to do that backward connection, it also generates 500,000 of, we call it pseudo wells. So it's each possible well that we can potentially drill in this area. We also use a sort of a machine learning technology to generate those pseudo wells. But basically, why it's important is because now, for every possible well that we'll ever drill in this area, we can find out the production results, and we can examine all kinds of relationships between geology, completions, well lengths, and production. And now, let me switch to, unfortunately, my tabs are under this bar here. Let me move it a little bit. Now, let me switch to this cross plot here. So what it's showing to us is basically the quality of our prediction. this is my actual 12 months production. And the one to the left is what machine learning model predicted for me. You can see that the quality is quite good. And one of the reasons is because it's good machine learning models. And actually, the data set, even though it's public, it's quite good. It's Canada, quite good and high quality data. What actually we're missing here, and if any of you would like to provide us that data, that would be totally awesome. But what we're missing here is a good data set on cluster spacing as well as well spacing. Unfortunately, it's fairly old Canadian wells. Back then, they didn't have a spacing that is tight enough to actually see the well-to-well interference. But those two parameters, honestly speaking, they're really missing. But anyway, we have geology, we have completions information, we have well length information. Probably the last one, the last crossplot I want to show you before we'll start examining the actual results of that machine learning modeling would be the reason why we cannot just use any sort of simple linear models. So this is a correlation between my completed lengths and total propant, two most valuable, two most influential parameters. The longer the lateral, the more propant we pump, the more the bigger production we're going to get. I mean, yes, it's all logical, but as we can see, the correlation is quite weak. The reasons is because all of those wells were geosteered differently. Those wells, they have different fluid loading. They had different geology, different average porosity. They had different stage spacing. So because of that, that correlation is not good and cannot be used for any kind of prediction. Now, let's go to actual production prediction and examining the results of that machine learning model. So what is happening here, I'm plotting a heat map of my completed length versus propant concentration. So the two most influential parameters. And the color here is my 12 months production per well. And as you can see, I have a lot of sort of rectangles here. Each of them corresponds to a specific completed length and propant concentration. On top of that, I have these bars to filter my data to a specific, say, porosity. So what I can say is, yes, for this specific completed length and this specific propant concentration, say right here, my 12 months production is going to be 9,000 or actually almost 10,000. But let me narrow down my porosity to sort of this. Say only, let me take only wells with very high porosity. And it will show me the prediction for those wells of high porosity. The beauty of this technology is that we still can see that interpolation here, even though it could be maybe only like 2 or 3 wells drilled with that porosity. But because we have lots and lots of those pseudo wells generated, we basically modeled all possible scenarios. We modeled all possible wells that could have been drilled in this area. So now we can pretty much play with all of those parameters and see how each of them influences the production. As for me, actually, Dylan?
Yeah, one question here. I was just thinking, so that one of the prime drivers that we're using here is that synthetic data from type well frac 1 to get that porosity. But if there's a situation where, let's say you had a quad combo that had been running, you had data from the heel, but you had something else by the toe, would you just run the model twice, or is there any way to interpolate between the models? How would something like that work?
Are you asking about the case when we have quad combo in the lateral?
No, it's if, let's say I have 2 type wells. I have a heel type well and I have a toe type well.
Potentially, yes, you can run porosity prediction based on each of those type wells and average them out or average them, weight them by distance. Potentially, that's something possible. But as a first approach, I would always just recommend to run it of the type well that we use for the geosteering to see if we have any type of correlation. And that would be, the first thing to do, if it makes sense.
Yeah, it does. Yep.
Okay, so again, now we're examining just possibly the most common and simple type of correlation, completed length versus proper concentration. Now, let's see, for example, whether fluid concentration or stage spacing influences my production performance. I mean, it's quite logical. Stage spacing, the shorter the spacing, the better the production. The longer the lateral, the better the production. And here you can actually see what is better, right? So for example, for this stage spacing, your production is going to be 72 thousandths. 12 months production. For this stage spacing, it's 95. So you can quantify what would be the results of making your stage spacing more narrow. Should you know, or if you know the economics, you can actually come up with the best economical scenario, right? Is what would be your maximum economic, the most economic well for this particular area. Same with fluid concentration, right? We can see that, we definitely can see here that the more fluid we pump, the better the well is. Even though so say for each of that bar, my proppant concentration stays constant, but my fluid concentration increases and production performance is getting better. We can always, filter down, filter down to certain porosity levels, because say in a certain area we expect lower porosities. We can see what kind of fluid concentration, we're going to have here. And the very last one is actually my favorite, is whether the geosteering matters. Whether does it really matter if we geosteer the lateral in the zone or out of the zone? Is there a correlation between geology and production? Luckily, yes, it is. Here again, we have our proppant concentration increasing to the right, and porosity increasing from top to the bottom. And as you can see, with the same proppant correlation, for each of these bars, as we go down, our production is increasing. And we can actually see by how much it is increasing, right? What specific value of the quality of my geosteering in barrels. And of course, if we have the oil price, we can convert it to something more meaningful than barrels. For example, for this type of porosity, our production is 63. 12 months production for this type of porosity, it's 94, 95 actually.
I could even see this being useful because one of the topics of conversation is what is an appropriate size of zone. Do we need to stay within 10 feet? Do we need to stay within 20 feet, 30 feet? It seems like this would be able to help us pick out what the appropriate drilling zone should be.
And there are, again, what we're showing here, so this particular heat map is a result of us applying machine learning to extract the information from the data. We won't be able to show any kind of heat maps like that if we just use a regular cross plots or regular data sets, simply because in most of the cases we don't have enough wells drilled, or we don't have enough wells drilled within this porosity. And actually by the time when we have enough data, it's probably already too late. So we could build these type of relationships, these 500,000 pseudo wells, using, I believe it's 60 to 70, maybe 65 wells that were drilled in that particular Canadian play. Of course, the more data we have, the better it is, the more accurate my machine learning model is. But as far as machine learning as a tool to find meaningful relationships from the data, and then being able to interpolate those and create those pseudo wells so we can examine the results, I mean, it's a perfect tool that we are using right now.
So another thing that comes to mind, and we've talked about it a little bit before, one of the big buzzwords that outside of the ones we already talked about is parent-child effect. And obviously, a lot of that is a result of spacing. But I've always kind of had a suspicion that some of that parent-child effect is due to legacy wells that were drilled maybe before geosteering techniques were as good as they are now. back when people thought drilling by seismic alone was actually an appropriate technique, or that the formation was so big it didn't matter where they were. And of course, there's also just sometimes the like the best geosteer in the world can sometimes still be wrong about where you are. Using this technology, and I was thinking maybe on some of those scatter plots that you showed, I wonder if we could look at a data set and then just based on production, be able to filter back and be able to say, all right, this well right here doesn't match up. Let's go look at it. What was wrong with it? And look at the geosteering. What do you think there?
Dylan, I have a dream to have that data set and actually show or actually prove or disprove what you just said. The only way to prove or disprove it would be statistics, right? To get geosteering data, to get completion data, to get frac data, frac heat data, all in one place, and then build those plots. As long as we have, 20, 30, 40, or 60, 50 wells with frac heats, I'm quite sure we'll be able to answer that question. And there are actually much more questions that I would like to answer. One of the concerning one would be, the never-ending discussion on engineered completions. Whether we frac our wells in a specific zones or porosity or places, or we just do it geometrically. Does it influence the production results? This would be the perfect technology to answer that, because yes, according to service company's presentation, all of those wells are always better. But is it better in reality? Is it better statistically? And if it's better, by how much it's better? What's the value of the technology?
Very, very interesting. Very interesting.
So yeah, that's actually the last machine learning technology that we wanted to demonstrate to you today. We keep developing new ones, not for the sake of development, but because, as I said, because we find them valuable, faster, and better for many different applications. If you have any ideas or data you would like to share with us, you're more than welcome. We are always happy to discuss.
Absolutely. Does anybody have any questions? If you do, go ahead and put them into the chat or into the Q&A. We can see either one of them, preferably the Q&A, really. And I'll go ahead and read them out and get Igor's opinion on them. Questions about things that we went over here, even ideas that are in line with the topic of the discussion.
Maybe Dylan, your opinion as well.
Maybe. So Rafi actually asks, this projection to bit, will it be able to help to predict the inclination and azimuth results after each slide? He means based in the drilling parameters during the sliding procedure. So like, once again, like basically looking at the tool face, will it be able to predict the yield of that slide?
That's exactly the purpose. Yes, of course, from the directional driller standpoint, that's exactly what it's doing. My explanation was mostly towards the geologists and geosteers. For them, the most meaningful information is just where is my bit and which particular part of the reservoir is my bit, right?
Right. And would that data then pump over to StarSteer to be used for correlation ahead of
course.
the bit? Okay.
Of course, that's the whole purpose. Yes.
Yep. A question, I'll need a little bit more clarification here from Chao Shun. He says, first of all, can we share the recording of this email? I wonder if he's sharing means the recording of this video. And this video, yeah, okay. The video will be on our knowledge base. So all of our clients will have access to it. And then there'll be maybe some discussion offline about whether this is going to be shared on YouTube publicly. That is yet to be determined. But it will definitely be on our knowledge base, so all clients will be able to see it. Other questions about the products, the technology, the ideas? Dave Baker, I know you're out there, and I know you got questions or comments at least. Let's see here. Well, we may not, you know how it is, especially with the weather stuff that we're experiencing here in the United States. We may not get the questions, and it looks like we did go a little bit over here. But I'll give them a couple more minutes. But in the meantime, Igor, I appreciate you joining the Third Thursday team here to come in and share some of your technical expertise on a topic that's really, it's at the front line of everything that we're doing in operations these days.
Always happy to.
Yes, sir.
Hope everybody enjoyed it.
Here's a slide from Mr. Baker. He says, "Can you tell slide or rotate?" Are you talking about with our? Could you elaborate a little bit, Dave?
I wonder if it's about this one.
Well, I'm guessing it is because that's right up his. Yeah, he's talking about rig state. Yeah.
Yes, David. Yes, we can. If it's most commonly these days, directional drillers, they use so-called drill pipe oscillation, right? Is when instead of just keeping the constant tool phase, they're rocking the pipe. And this is the hardest drilling status for identification, because instead of just constant 0 RPM or something close to 0, you have RPM that is just constantly, going up and down. So that's where we use, answer to your question, yes, we can. And we use machine learning to identify it.
Yeah, a day is always good for a good question. I know it's got to be killing you that the audience is muted here, but certainly we could probably set up a time when you and Igor could have a conversation. Maybe once the world goes back to normal, maybe even a lunch or something. We have a question from Aaron Jackson. He asks, "Are you going to be able to apply that machine learning or any machine learning algorithms to imported seismic data?" All right, big question. Yeah. Star size. Here we go.
Yeah. It's like the question about humanity. Yeah. Can we? Yes, we can. The problem is that we don't have support of seismic in any of our products yet. Having said that, we are rolling out geomodels in upcoming StarSteer, and we'll have a support of three-dimensional geological models. So the next logical step would be to add support of seismic. And once we have the support of seismic, for sure, as a geophysicist by education, I want to do something with that seismic. But it's probably, as of today, it's mostly waving the air instead of just, waving the hands instead of just saying that we have something. Yes, as of today, we don't. Eventually, probably we will.
Yeah, for sure, this is something that it's less frequently requested now than it used to be. But just the ability to deal with seismic within StarSteer is more than a JPEG is something that's been requested. So that would be, if we moved into that direction, that would be a massive addition. And then I guess there'd be no need for any competitors after that. Everybody else could just go home.
Seismic, Dylan, if you think of seismic, it is still there, right? Permian is very well covered with 3D seismic. You go for it, it's very well covered with 3D seismic. Same with Williston Basin, DJ Basin. So it's there, it's used for geosteering or other things. So it's very much needed technology.
Now, Chaoshan asked again, he was wondering if you could speak about the connection between slides 6 and 7. So 6 is the stretch and squeeze, add noise in the vertical part of the well, and 7 is the correlation panel. So
6 is how, and 7 is basically why. So 6 is how we build learning, how we build data sets to teach a neural network how to correlate wells with each other. As I said before, we basically take an original log, we add noise and bunch of problems and scale changes and all kinds of things to that log, and we use these two pairs of the log to train a neural network. And then once it's trained, we use the actual data, and this is the actual data: actual type well, actual lateral well, and then we correlate basically piece by piece. Take a small piece of this lateral well, correlate it with all possible pieces of the type well, and once the correlation is good, according to the neural network output, once the correlation is good, we put sort of a red dot. If it's bad, we put a blue dot. So then you basically can draw this two-dimensional image where the red line will correspond to the best correlation between both of those well logs. And once we have it, we can basically say that, yes, this particular gamma ray thing, gamma ray spike, be correlated with that particular gamma ray spike. And once we go to the correlation panel, we can just correlate. We can say, okay, this well top, find me the same well top on the other well, and we can just correlate it well to well. As I said, this autocorrelation functionality is not in StarSteer yet, but for sure it will be there soon.
Cool. We have
watch for updates.
I'm sorry about that. Actually, Igor, could you flip back once the slide so we can look at spectrum again? And so for those of you guys who don't know, that image you're seeing there, where we're talking about the red and the blue dots, this is actually something that's part of the assisted geosteering package. It's called Spectrum. And it's something that I am a huge fan of, because not only is it visually showing you what the assisted geosteering tool is doing, but it is a way for you to see on a single two-dimensional display all of the potential interpretations. So frequently as a geosteer, I feel good if I'm keeping 3 to 4 interpretations alive. But the AG tool is looking at thousands and thousands of different possibilities. And so I can just visually look at that. And if I happen to see one, even if it isn't the one AG particularly likes, it's letting me see this is all the options I should be looking at. So I might just make a copy of my interpretation and just manually make an interpretation that doesn't necessarily align with what AG thinks or what I think, but it's just another possibility. So it's a great way to be able to bring that whole package, the human and the computer together. Now our very own Stephen Clark has a question. He says, could you envision machine learning AI being able to identify sequence stratigraphy relationships in logs? More simply, could it deal with lateral stratigraphic variability?
Potentially, yes, but I guess the question here is more into, so machine learning is as good as your training data set is, right? So if your training data set is having those issues, and it has, the well tops, or it was correlated properly, if you can train your data using that data set, if the training result is good, then yes, we can do it. We can recognize faces as long as we have a few billion faces and their names associated with them. That's why nobody else but Facebook can recognize faces, simply because they have the data, our data, right?
Facebook, the social dilemma. Okay, well, do we have any more questions? I don't have any more listed here, but if anybody has some last questions while we have Igor here, go ahead and put them out there and I'll read them to him. In the meantime, we will be, of course, having a webinar next month. We are looking to have StarSteer 2021.1 out here. Are we expecting that in the next month, Igor? When do we think that will hit?
It's probably, we'll be able to show it, but I would prefer to do it the months after. Okay,
so check. Well, we'll have a third Thursday webinar, of course, in March. We'll also have one in April, and that April one will be going over the new release 2021.1. If any, let's see here. Oh, no, that's the same question. So I think that's the end of it. Igor, thanks very much for joining us. And we'll bring you back the next time we have something highly technical for you to speak on.
Thank you, Dylan. Thank you all for participating. Have a great day.
Yep, you too, Aaron. Thank you.